Hello.
Hello.
Okay, let's wait a couple of minutes so the rest of the people can join. Okay. Well, let's start then. First, I want to ask how are you going with the homework so far? Is anybody of you having any trouble picking the topics or making the assignments?
Well, I'm gonna start with assignment 2. I haven't started yet, so.
Okay, perfect. That's great. I have received out of works on the assignment 1 already, so good job. I will be coming back to you with comments if I have any and such. So today I'm gonna start talking about the class project, which is going to be done in groups. You all send me your groups this week, so that's perfect. 1 second. Okay. So I'm gonna start with the guidelines for the project. As you know, the project is the most important part regarding the grades of this course. You will have, if you get the grade for the project will decide whether you have a 3, 4, or 5. So if you don't have a 5 on the project, you cannot have a 5 on the course. And of course, so you need to have 2 high grades to get that grade. So for example, you need a 4 in the project and a 4 on one of the other assignments to get a 4 in the course, and so on. So this is like big, this is the big assignment for the class, and it has like the paper and the presentation at the last class. So yes, I expect you to be more to do more work in this class project than in the assignments. When is the last class? The last class is 1 second. I think it's in 4 weeks. Give me a moment. So the last class is on the 11th of March. Sorry, 11th of March. So we have this class today, 2 more classes, and the last class on March the 11th. Okay. So what the project is about, you have a list of research articles in ATM, and they are divided in topics, and these are the topics that we choose. We have capacity, path generation, robustness, planning in the face of uncertainty, dynamic airspace configuration, ATM, remote tower complexity, air terminal operation, and user-driven prioritization process. So these are the topics. This is the list. I'm gonna share the list with you so you can see it. So this is the list of topics, and for each topic we have a list of articles that you can choose from and read whatever interests you the most. Have capacity, path generation, robustness, etc. Okay, so you have this list with all of information. And what I want you to do is to choose a topic and read some articles on that topic. And you must formulate a new optimization problem related to the topic. So this is the big part of this project. You will have to be creative with your problem. You have to come up with a new problem. You have to formulate the optimization problem, etc. So read about the topic, read a bunch of papers. You can, of course, be inspired by other problems to come up with your own, maybe making some modifications or adding new things. So yeah, come up with a new optimization problem and write your assignment about it. So the new optimization problem that you choose or that you come up with must be relevant to ATM, of course. It must be based on the articles that you read. And of course, if it's a small problem or something that's not very realistic, but that's something that makes sense, that's okay. We are not expecting you to do to come up with a big project or anything. Just find something relevant to ATM and write and come up with an optimization problem about it. So these are some of the instructions. Give a name to your problem. The problem must not coincide with any other problem considered and discussed in this class, including problems from homework 1 and also homework 2. Of course, you're not limited to the list that I shared with you. You can find any other articles you want, and also you choose other topics. But if you find an article, send the link. Send me the link, and I will tell you if that's okay to use. Again, the same for slides. If you find a slide for an article, also share them with me so I give you my approval. And again, you can go off the list. For example, if you find more recent articles. And again, because you're going to be basing your project on those articles, it would be good if I give it a look beforehand so you don't get too lost. So if you find anything new that's not on the list, please send me the link. And also you can choose other topics, of course. So the essay, you must do 2 things. First, you have an essay that you must write, and then you have a presentation that will be given at the end of the course on March 11th. That will be 15 or 20 minutes. Just choose one of you to do it, or if you're a group, you can divide the presentation in intervals, so every one of you can present whatever you like. So the essay must contain the following. First, an introduction. Then you have to define your model, the problem statement, add some sample instances, a solution suggestion. This part is optional. You don't have to do it because we haven't seen in this class optimization techniques per se. So you shouldn't, this part is additional. For example, if you're basing your project in a paper that already suggests a solution approach, it could be simple to just use the same. And also, I want you to give you some. I want you to give me some what the difference are between what you've done and what's in the literature. So let's go one by one. First, the introduction. You have to describe the topic. I have a question. How long should the class project essay be? There's no limit here, and I don't have any suggestions. Just whatever you find the most appropriate. Not very long. You will see when I go through this. Maybe 1 page for each of these, or half a page for each section. You decide. It's up to you. Okay. A little longer than the assignments, of course, because you have more work to do, but nothing super long. You decide. Okay, we have for the introduction, you have to describe the topic. So what is your problem about? That's very similar to what you did in homework 1. Just describe what you're going to be working on, and then you must state your motivation, why it's important, how does this problem solve one of the challenges in ATM, how is relevant to the future of ATM, or how is it linked to CSR efforts, whatever. And then you have to do a literature review, which I would say is quite important. If you're basing your project in a given articles, you must give them credit and you must describe what those papers do, what those authors are talking about. So this part is quite important. First, you have to say which articles is your project based on, what has been done in the past by those authors, and what was considered in those papers that you read. So if you decide to use a couple of papers, just describe them and give them the credit that they need. Then you have the model. The model would be to cast your problem in a mathematical framework. You must be precise and be rigorous, as we discussed in class. You must state the simplifying assumptions that you make. For example, imagine that you're working with aircraft trajectories. One possible simplifying assumption could be that the aircraft fly with constant airspeed. Also, another assumption could be that you don't consider uncertainties. You can assume relationship between variables, etc. So all the simplifying assumptions that are relevant to your model, you must describe in this section. And also find a minimal non-trivial model. That's something that we talked about already. The problem should be simple enough to develop a model, but it should not be trivial. And this question, that what makes the problem non-trivial, we already discussed in previous class. So just make describe a problem that's not too simple, describe a topic that's not too complicated, something that you can model, something that it's not trivial. And if you find trivialities, you can always add restrictions or constraints to your problem to not make it trivial. So this could be an example of a model that we discussed last week. In the problem that we discussed in last week about the closure of an airspace, we defined the model for the aircraft that are affected by that closure. So that could be the equivalent. If you have, imagine that you're choosing this topic for your project. In the section about models, you should write something like this. Identify your variables, give them a mathematical expression, and again, in general, have a mathematical expression of your problem. Of course, this one you cannot choose because we already talked about it, and also it's very simple. But yeah, something, take this as an example, just some mathematical formulation of what you want to do. And of course, you can base your mathematical model in the articles you choose. And so read them carefully, and I'm sure you will be able to do this, no problem. Then we have the third part, which will be the problem statement. And this is like the most important part of your project. Of course, the others are important, particularly this one and the introduction as well. But the problem statement, because we spent a whole class talking about this, I expect you to do it very well. And also you have practice with homework too also. So this is an important part of the assignment. So the problem statement is what we discussed in class already, the input, what kind of objects are given, any assumptions on the input. That's a typo over there. Then we have outputs, constraints, and objective function. All that we discussed last week. You should build your problem gradually. You have two approaches. One would be to do what we did last week and start with a simple statement and build up from that. Another one is you can come up with a very difficult problem and you start simplifying it. I find that this second thing is usually what is, I think it's more common to think of a very difficult problem because ATM is a complex environment, so you always have to make simplification in order to solve things. So if you're stage your problem and if it's too long, if it's too complicated, if it doesn't fit on one page, yes, you should present the problem in stages. First, create a simplified version of your problem. Put this simple problem in one page, and in different pages you can elaborate more on the inputs, the constraints, the outputs, etc. So first, if you have a very complicated problem, simplify it and then elaborate on your simplification. Then we have the sample instances. We talked about this last week as well, so I'm not going to talk much. But a sample instance, as we saw last week, is give a set of values to all your items in your input and output, and yes, check consistency, etc. So how many sample instances should you include? Well, you should include as many as people are in your group. So if you are 4 people, you should include 4 sample instances. If you are 2 people, include 2 of them, okay? The idea is that each one of you can participate in that problem, in that assignment. So that's a good way to divide the work. And this is the example that we saw the other week. So I'm not going to talk much about it. Then we have the solution suggestions. What would you suggest to solve the problem? What optimization techniques would you use? Of course, you don't have to solve your problem. That's something that in most cases is very difficult, so we don't expect you to do that. And also look at papers for ideas. If you are basing your project in one of 2 papers, the most normal thing that will happen is that those papers already use optimization techniques. So you can suggest to use those in your problem as well. This is not graded because we haven't seen much about this and we have not worked with this. We are not going to grade your assignments on this, and you can skip this section entirely. And of course, crazy ideas are okay. And finally, you must include the differences from the literature. First, on the model, how is their model different from those considered in the literature? For example, maybe in the literature, the model is stochastic, but you simplify it and use a deterministic model, or with dynamic and static, etc. How does your model change from the article that you choose to base your project on? And also you have to state your difference of the formulation. So for example, if you consider a different objective function, you must say how is that objective function different. If you have new constraints or less constraints, how different is your new problem from those problems that have already been studied. Of course, if you come up with an entirely new problem, still you have to say what is new from what you've done. Okay. So some notes, some guidance. First, you have to be rigorous. You have to define all your objects. You have to say what kind of objects are in the input, what kind of objects are in the output. We talked about this last week. Are those object functions, numbers, schedules, sequences? You must state what your inputs and outputs are. And also follow the rules from the lectures. Use this format. We have two available formats, so use any of those that you like. What kind of objects you have, and again, the problem shouldn't be too simple. You are the judge to that. And finally, don't what we talked about last week, don't confuse objective and objective function. And basically, this is it. This is like a more complicated version of homework 2, because in homework 2, you just have to read an article and say and state your optimization problem. In here, you have to be creative. You have to come up with a new optimization problem, which is going to be difficult, but that's something that, because that's why it's a group project, so you can share ideas and you can read more papers between you all in order to come up with this new optimization problem. So one anecdote that Valentin told me about is that in some years ago in this class, for the class project, students chose remote towers operations, and the assignments are for traffic controllers to these remote towers, and they did their project on that, and that became a line of research for the whole group, and now they have papers about it, they have projects about it. So it's something that was very creative and very relevant, and it inspired a whole new line of investigation within the department. So that's something that I hope inspires you to do something relevant to ATM, do something new, and do something creative. Okay, I'm sorry, I'm having some noise in the background. I hope it's not too disrupting. So finally, for the submission and deadline, again, send the essay in PDF format to my email. You can also send the presentation, but the presentation you're gonna give live on the last class. The assignment is made in groups, and the deadline is the last week, the last class of the course, which is week 10. You will present your work in the last class as a presentation, which is going to be 15-20 minutes, and finally these are the grades. So you sent me a lot during this week. You sent me your groups, and this is what I have so far. Please tell me if there's someone missing, if I got something wrong. I know that it's a student that is not in a course already. I don't know if he's here right now. So please look at your groups and see if everybody's there. Okay, from your silence, I'm assuming that everything is correct for the groups.
Yes.
Okay, perfect. So, okay, I have one student that didn't send me their groups. So I don't know if you talked. I'm not sure if it's a she or a he. I don't know. This name is Mercy Ha. Is he or she here? Okay, well, I think they are not. So they didn't find the group. So I was hoping that one of these three groups that have the least amount of people could have her in the group. So please talk between you, and if you come up with a solution, please let me know. But of course, if this student don't find a group, it's not. I mean, it's not your job to find a group for her, so or for them. So please let me know if you have any new information. So far, we're gonna let this be with these groups, and yeah, if you have, that's all for these guidelines. Do you have a question about the project? Okay. I guess that you don't. If you have any questions after this class and when you start making the project, please send me an email. I will try to help you with what I can. So yeah, that's all on the class project. So good luck with that. Okay, and now I'm going to start giving you the following lesson, which is going to be on aircraft trajectory optimization. So this is the last class I'm going to be giving personally. The following class and the class after that are going to be Valentin is going to be giving them. But again, if you have any questions or anything that I can help you with, just send me an email and I will be available. I will be in the last class on the 11th of March to listen to your presentations. But this is yeah, the two following classes are on capacity, and I think on economical aspects of ATM are going to be given by Valentin. So this is the last class that I'm going to be the last lesson that I'm going to be given to you. This is aircraft trajectory optimization, which is a very important topic in ATM. We are always talking about efficiency. We are always talking about using less fuel, etc. So aircraft trajectory optimization tries to tackle those problems. Also, it's not always about efficiency or the environment or whatever. Aircraft trajectory optimization is important because it's a useful tool for airlines and for people working in the aviation industry, because it saves money. I mean, fuel costs money, and if you can use less of it, your flight is going to be cheaper. And so that's trajectory optimization. It's a relevant topic in ATM in general. So this is what I want to see today. First, an introduction on why trajectory optimization is important. This is nothing new. We have already seen this in the first 2 weeks. A little bit of introduction of flight mechanics. I don't know if you know. I don't know if you have worked with flight mechanics or with mechanics at all.
No, not so much.
Okay. So this is
Not
just
at
an
all.
introduction. It's just an introduction, so there's nothing you have to memorize or to learn. I mean, you can give 3 or 4 courses on this and still have material. So I just want to give you an introduction on why is it important for trajectory optimization, and also for you to understand the complexity of the problem. Then we're going to take a look at trajectory optimization per se, a little bit on aircraft conflict detection and resolution, and finally, trajectory optimization under meteorological conditions. So let's start with a little introduction on why is trajectory optimization important in the future of ATM. So as you know, this is something that we already know because we have been we have been seeing what Cesar wants to do in this class in the first 2 weeks. So we know that there is a concept which is trajectory-based operations, which is a key concept in the future of ATM. So the trajectory-based operations, this is just a reminder, the trajectory-based operation concept will enable airspace users to operate their preferred trajectory from gate to gate in order to satisfy their business and operational needs. So how do you determine what is the user preferred trajectory? When you do that using aircraft trajectory optimization. And also we have another concept, which is the 4D trajectory concept. This is a concept that it's very related to trajectory-based operation, and it's basically the sharing of information of trajectories from the aircraft users to the air navigation service providers and all the other users, all the other stakeholders that may need that information. So in the 4-dimensional trajectory concept, the trajectory of the airplane is going to be given by a detail optimized for the trajectory, which means you are going to have points in a space, in 3-dimensional space, plus time. Okay, and this is going to be shared with air navigation service providers, which are responsible for allowing you to follow your preferred trajectory. This figure over here, we have an example of what a 4D trajectory would be for each important waypoint in the trajectory. We have, not only we have the position, but we also have the time. So the idea is that this information, this 4-dimensional information, is shared between all the users of the airspace. So by using trajectory optimization, we can obtain what this 4-dimensional trajectory would look like for our interest if we were an airline or another airspace user. So in this lesson, we're going to focus on commercial aircraft, which are the most popular. I mean, right now they are more. We have more traffic of commercial aircraft than any other type of aircraft. So, of course, this applies to commercial aircraft and not, for example, the military. They have their own missions, things that they want to accomplish, and they are not always consume the less fuel or fly this faster. They have their own missions, and this kind of the kind of optimization or the kind of trajectories that they want are not the same as commercial aircraft. And also, we are not going to be looking at small drones or anything like that, because they, of course, have different missions as well. So, as I said, we are going to be focusing on commercial aircraft only. So let's talk a little bit about flight mechanics. What is it and why it is important to aircraft trajectory optimization? So flight mechanics is the application of Newton's laws to the study of aircraft trajectories, which is also called performance, stability, and control. So how does the aircraft move? Equal to how would we apply the Newton's laws to any kind of object in the ground or any place else. If we focus on aerial vehicles, we're going to be talking about flight mechanics. And flight mechanics in general include also things like rockets and gliders, how do you say, helicopters, all those kinds of aerial vehicles. But as I said, in this class, we're going to focus on commercial aircraft. And there are two main parts of flight mechanics. The first part, I'm going to start with the second one. The second one is stability and control, which is the study of the motion of the aircraft center of gravity relative to the ground and to the motion of the airplane. So this one is not so important for us. This is important for designing the aircraft and such. But what is important for us in trajectory optimization is the trajectory analysis. So this part of flight mechanics is the development of formulas and algorithms for computing in each segment of the mission, which are takeoff, climb, cruise, descent, and landing, performance quantities such as the distance traveled, the time elapsed, the fuel consumed, etc. So these are tools that allows us to compute for a given mission how much fuel do we need, how far are we going to be able to travel, how long is this mission going to last, etc. So you can see that this is that flight mechanics can be very useful in the context of ATM, in the concept of designing your flight paths, designing your trajectory in general, also for air traffic flow management. Also has to use this kind of tools to predict what the trajectories are going to be, etc. So this is quite important in aircraft trajectory optimization. And we have something in flight mechanics, which is the point mass equations of motion, which gives us a relationship between the aircraft state, which is their position of the aircraft, the velocity of the aircraft, and the mass of the aircraft, and the forces affecting the aircraft. In the context of our class, what we want to do is to formulate optimization problems. What flight mechanics would do is to give us the model for the optimization problem and also give us the objective function. So if your objective function is the fuel consumed, for example, if you have a problem which has an objective of minimizing the total fuel, your objective function you will have to construct using tools from flight mechanics. So this is an example, a diagram of what flight mechanics does. You have the equations of motion of the aircraft, which is based on the Newton laws. And to this you feed some initial conditions, for example, the initial position of the aircraft, whether it's in the ground or already flying, the initial mass of the aircraft. If, for example, you are looking at an aircraft that hasn't departed yet, you have to know what the weight of the aircraft is empty, what the weight of the passengers are, the weight of the crew, the weight of the fuel that's being feed into the aircraft. So all of those initial positions are going to conditions are going to affect the aircraft trajectory. Then you have the atmosphere model, because aircraft do not aircraft behave in a different way depending on the atmosphere they are in, depending on the temperature, the pressure, etc. In general, there is something that is called the standard international atmosphere that is used, but it can be any other atmosphere model that it's needed. And then we have the aircraft model, which gives us an idea of how the propulsion works in that aircraft and what the aerodynamics are of that aircraft. So of course, this equation of motion are going to depend on these parameters, because if you try to set a relationship between forces and positions, you need to know how those forces affect those other variables, and you only can obtain that using some propulsion models and some aerodynamic models. And finally, we have something that is called flight constraints. So of course, the aircraft are going to behave like any other object in the universe is going to behave by the Newton laws. But if you want to know how an aircraft is going to behave in a given segment, in a given mission, you have to give it flight constraints. So what kind of mission are we going to try to perform? This kind of mission can be, for example, a flight which is done with a constant altitude, or for example, an ascending trajectory from after the takeoff. So all those things are going to be included in the flight constraints. So with all these 4 information boxes we have, and we fit to the equations of motion, and through integration we obtain the aircraft trajectory. Okay, so this is a very complex topic. There are a lot of equations, a lot of physics and mathematics. So it's not something that we can see today, but I just want you to know that this model of aircraft exists, and that this is what is behind aircraft trajectory optimization. So just to give you an idea of what flight mechanics, of how flight mechanics work, I want you to give you some little concepts. Of course, this is not the subject of this course, so if you want, you can disconnect a little bit, but I think it's something that it would be nice to know if you ever encounter any of this. So in flight mechanics, the aircraft is considered a point in the center of gravity, which has 3 degrees of freedom, and there are 3 main forces that affect the aircraft. The first one is, of course, the aircraft weight, which is pointing to the earth, of course. Then we have the thrust of the engines that goes in the same direction of the velocity of the aircraft. And also we have the aerodynamic forces, which is what allows the aircraft to fly. We have the lift, which is the force that is made by the winds and is going upstairs, that is conserved in the wave. And this is the force that keeps the aircraft in the air. And then we have the drag, which is the resistance of the air, basically. So if there were no drag at all, an aircraft could fly without stopping, the same as a car. I mean, we have a force that is making the aircraft to slow down, so we need the thrust of the engine to contrast that force. So these are the 4 forces that affect the aircraft, and using the equations of flight mechanics, which is something like this, we can obtain what the positions, the velocities, the orientation of the aircraft, and the weight is with these expressions. Of course, this is not the subject of this course, but I want to give you an idea of what this kind of material is useful for. So if you, for example, want to know how far are we going to travel given a given an amount of fuel. For example, you will have to integrate these equations in order to obtain that performance, that variable. So using flight mechanics, we can answer optimization questions like, for example, given a particular aircraft, a given atmosphere, and a given initial conditions. What is the amount of fuel, given an amount of fuel, what is the maximum distance that we can fly? For example, that's an optimization question that we could formulate. Another one could be, given an amount of fuel, what is the maximum time that an aircraft can spend flying? So that's something that we also would want to consider. For example, another optimization question could be, given a distance between 2 points, what is the minimum amount of fuel necessary to fly that distance? Or, for example, given 2 points, A and B, what kind of mission? In general, we have to define the velocity profile, the altitude profile. Must the aircraft maintain to fly from A to B with the minimum fuel? So all these questions can be answered through flight mechanics, and it's going to give us a model. It's going to give us the objective function in order to answer all these questions. Another optimization question could be, given a particular mission, what kind of aircraft fly the mission the fastest, longest, or with the minimum fuel consumption? So this question over here will be into the realm of aircraft design. For example, to design the aircraft, we have to take into account the takeoff weight, the engine size, or the wing size. So which kind of aircraft is going to be the best for a particular mission? That is something that aircraft design has to work with. But we, in ATM, are going to be looking at this question over here. We already have our aircraft, or aircraft that are already built. It's not our objective in ATM is to make those flights more efficient, but not to say what kind of aircraft can or cannot fly. So this could be the objective of trajectory optimization, to try to answer all these questions. So let's go for trajectory optimization. So right now, I think it's a good time to make a little break. So maybe we can come back in 10 minutes or so. First, do you have any questions about what I told you so far? Okay. Okay, perfect. We'll see you in 10 minutes then.
Okay.
Well, hello back. Okay, let's finish them. Yeah, so that was all on flight mechanics. I hope it was not too much. It's a very dense topic, and if you want to study it, it has a lot of literature about it. But as I said, it's not the subject of this course, so we're going to leave it behind. Just be present that the objective function and the model, if you're working with trajectory optimization, always comes from flight mechanics, okay? Then we have aircraft trajectory optimization. So we can classify different trajectory optimization problems depending on whether we are in one flight segment or another. In general, we can separate these 5 different segments, which are first takeoff, the climb, the cruise, the descent, and the landing. These points over here, the TOC, top of climb, and the TOD, top of descent, are points that are, I think we are going to be hearing a little bit about them. They are the highest point of the climb, after which comes the cruise, and the top of descent is the higher point of the cruise, after which comes the descent. So basically the beginning and the end of the cruise segment. Usually when we talk about trajectory optimization, a lot of work focus on the cruise, some of them focus on climb and descent, and we don't focus on takeoff and landing. Why not? Because takeoff and landing take a very, very small part of the whole aircraft operation. So if we want to optimize the use of fuel, we're going to be focusing more on cruise, climb, and descent than in the takeoff and landing phases. And in particular, the cruise is the longest part of a flight in general. So it's very common to focus our optimization efforts in that part of the cruise, okay? That is why I have this little thing over here to indicate that the cruise is much longer than this. And another way to classify trajectory optimization problems is to look at the objective function of the problem. So for example, we can optimize the flown distance, which is also called the range of the mission. We can optimize fuel consumption, flight time, a combination of time and cost. This is one over here, is a combination of time and fuel. And then we can also optimize our trajectory attending to environmental concern. Oh my god, another typo over here. Concern. For example, the noise. So depending on which objective function we are working on, we're going to have a different problem to solve. So there are 2 main methods to tackle trajectory optimization, just so you know them when you see them. The first one is the parametric optimization theory, in which you take the variables of the trajectory and use them as parameters that can only take one single value for a given set. For example, some parameters that you can use are the speeds, the altitudes of the waypoints of the trajectory, the angles at given points in both time and space. You can also use the trajectory waypoints coordinates, or the top of climb and top of descent. So just take given variables that describe the trajectory of the aircraft, and those are going to be your decision variables. Then we have the optimal control theory, in which we no longer have variables that can take one single value, but the output of our problem are functions of time. So using optimal control theory, we can obtain functions like the position of the aircraft or the aircraft velocity as a function of time, and thus are the output of the optimization problem. The resolution techniques that are needed to solve these problems are quite complicated, I would say. It's not something that we would tackle in this class, but just so you know that we have two different ways to tackle the problem. Either we treat the trajectory variables as parameters and optimize those parameters. So the output of our problem would be that trajectory parameterization, or the output of our optimization problem is a function. Okay. So if we look at the objective function, we can, in general, the most popular objective functions to consider, of course, they are not the only one. We saw that we can optimize while taking into account environmental reasons, or maybe you are interested in flying the longest. I'm sorry, the farthest. But the more popular ones, I would say, are the minimum fuel, which is obvious. Why is it popular? The objective is to perform the mission with minimum fuel consumption, and it has economical benefits for airlines and also reduce emissions. So this is a very popular objective function. The other one would be the minimum time. The objective is to perform the mission in the minimum time possible. It has also economical benefits for the airlines, for example, in the crew salaries, if they have to pay people less for being less time in the air. That's an economical advantage. Not only fuel is, so not the cost of a flight is does not only comes from fuel. It also comes from the crew, and also all the taxes that the airlines have to pay to fly over a given airspace. So for example, if an airspace is very expensive to fly on, they may want to fly over a different airspace, even if they pay more for the fuel or something like that. So not always we try to think of minimum fuel. Also, minimum time can also be beneficial. And also it gives us a better passenger experience. If you are going to make the flights shorter, of course, it's a better experience for the passenger. And there are some kind of missions that require this time to be less. For example, in business trips, people are more, how do you say this? People are okay with paying more money for those flights if they are going to take them fastest to their destination. So they have to consider what the time cost is and the fuel time is, and the fuel cost is. So this is when the direct operating cost appear. So this direct operating cost is something that is used by airlines, and it's a cost that is a combined cost of fuel consumed and time. It's usually abbreviated as DOC, and is the sum of the consumed fuel and an index that is called the cost index times the time of the mission. So this cost index measures the relative importance of each cost. So if the cost index is 0, that means that the time that we are in the air is that it doesn't cost anything. So we would be looking at a minimum fuel trajectory. The higher this cost index is, the more importance the time flown has on the cost of the operation. So airlines have to take into account both costs, and they try to decide what cost index is more beneficial for them. Either they want to spend less on fuel, or even they want to mitigate the costs of taking longer flights. So this direct operating cost is usually a very used objective function in trajectory operation, in trajectory optimization, sorry. So this is something that airlines use to optimize their trajectories, and if you see research regarding trajectory optimization, you're going to be seeing this direct operating cost a lot. So this could be an example of an optimization problem for a single aircraft using the notation and the formulation that we have used in this class that we used last week. So the input of our problem would be a set of parameters and equations that gives us the aerodynamic and propulsive aircraft model and also the atmosphere model. Then we have as an input a set of equations that are indicating the flight segments and a vector of initial aircraft conditions. The output of our problem could be, for example, it can be anything you can imagine, but for this particular example, the output could be a set of functions depending on time, which are the optimal Mach number and the optimal altitude profiles. The constraints that the flight constraints must be satisfied, which are this one over here, and the objective function could be, for example, the direct operating cost. So this is how a simple statement of the trajectory optimization problem in a way that we saw in class. Of course, in here we don't have the model. The model could be something very complicated and would be something that is based on on flight mechanics. But this is what our optimization problem would look like from what we saw in class. So now we're going to see how we can optimize the different phases of the flight, which are, we're going to be focusing on cruise, on climb, and on descent. So it has been proven, it's a result in the literature that if you want to optimize your cruise, the optimal trajectory is something that is called a cruise climb. So from the definition of a cruise climb is a climb technique employed by an aircraft, usually at a constant power setting, resulting in an increase of altitude as the aircraft weight decreases. So if you take those flight mechanics equations and you optimize the direct operating cost, you obtain that the optimal trajectory for the aircraft to fly is a cruise climb. In a cruise climb, the aircraft is losing weight because it's spending fuel in their engines, and as the aircraft weighs less, it takes an ascending trajectory. And it has been proven that using this kind of trajectory, the fuel consumed, the time that it takes for the aircraft to fly is the optimal. But as you can imagine, this cruise climb is very difficult to perform in an operational environment. Usually what is better to control, what is easiest to control for traffic controllers and for pilots is to fly at a given high level. So usually this cruise climb is approximated by something that is called a step climb. So in a step climb, we will try to approximate this optimal trajectory, which is the cruise climb, in a series of level flight, a little climb, some other level flight, climb, level, etc. So this kind of configuration of trajectory is easier to implement in an operational environment. You ask for permission to fly from one flight level to another, but it's still more more optimal than flying at a constant altitude for the whole flight. So this is for the cruise. If we take a look at the climb and descent operations, it has been proven that the optimal vertical profiles take the form of continuous climbing and descending paths. So from ICAO, we have these two definitions. Well, ICAO didn't invent them, but they are two well-known concepts in aviation, which are the continuous climb operations and continuous descent operation. These two are the optimal ways to both climb and descend. So in continuous climb operation, it is defined as an operation enabled by airspace design, procedure design, and ATC facilitation, in which a departing aircraft climbs without interruption to the greatest possible extent by employing optimum climb engine thrust at climb speed until reaching the cruise flight level. And on the other hand, we have continuous descent operations, which is the same, an operation enabled blah, 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 in which an arriving aircraft descends continuously to the greatest possible extent by employing minimum engine thrust, ideally in a low drag configuration prior to the final approach fix or final approach point. So what this means is that what the aircraft wants to do in order to consume the less fuel, in order to do the most optimal flights, is to continuously climb or continuously descend. These kind of horizontal segments are not efficient for the aircraft. In particular, in the continuous descent operation, CDO, it's important to notice that the aircraft are going to be flying with the minimum engine thrust. So the minimum, if one could say, okay, if you want to descend, why not turn off your engines entirely? I mean, you don't need additional thrust because you want to descend and you want to decrease your velocity. Well, this is kind of true. In fact, there are some airplanes that are called gliders that don't have engines at all, and they use these continuous descent operations to glide through to the destination. But in a commercial airplane, this is not possible. It's not possible to have zero thrust at all because you need some. So the engines are not only giving you thrust to keep flying, but they are also providing the energy for all the avionics or the mechanical and electrical systems that are in the aircraft, or the telecommunications, etc. So they usually fly a minimum engine thrust, which is not completely zero, but it has the less consumption of fuel by the engines. So these are the two operations that would be optimal combined with a cruise optimization. Ideally, we will have a smooth trajectory with no levels. So what about aircraft that can fly continually? Well, I don't know. To be honest, it's the first time I heard about Sukhoi Superjet. Maybe you can elaborate a little bit and tell me and your colleague.
No. I just I have heard something about it's a Russian aircraft, but passenger aircraft. But I heard something that its engines are so weak that they can't like climb continuously. They need to do it in steps because their engines are so weak. So I just wondered if an aircraft has weak engines, does it mean that it must climb in steps, or do you understand what I mean?
Yes, but I'm not sure how to answer you. On the top of my mind, I couldn't say that it matters. Like, ideally, even if, I mean, the most effective way to fly is always do a continuous climb. So I'm not sure how weak or how different these engines must be from regular aircraft. So I don't know. I cannot give you an answer, I think. But I will take a look, and if I come up with something, I will tell you.
Okay.
But I mean, if a normal aircraft is using their engines less by doing a continuous flying operation, because that's what an optimal fuel trajectory is. You use your engines more efficiently. I don't see how a weak engine would benefit from not doing that. But as I said, I cannot answer you properly. Okay. So this is for continuous climb operation and continuous descent operation. So these are some of the benefits that continuous climb operation and descent operation have. We have more fuel efficient operations. We have reduction in the pilot and controller workload, because if you're doing a step climb or a step descent, you have to keep communication with the air traffic controllers. Okay, I'm flying in this flight level, communicating the points on which you are descending and such. But if you're doing a continuous climb or continuous descent operation, you just have to say, okay, this is my descent path, and that's it. Then we have a reduction in the number of required radio transition, which is a consequence of the thing that I just said. You have to communicate your positions and your points much less. Reduce fuel burn, aircraft noise mitigation. Then we have a potential benefit could be that some flights are not possible to fly because they don't meet the noise limitations. So by using continuous descent operation or continuous climb operations, by reducing this noise, those aircraft would be able to fly. So more aircraft, more flights could be able to be accommodated. Then we have a more efficient use of airspace and a more consistent flight paths and established approach paths. So these are benefits that ICAO has identified to continuous climb operations and continuous descent operations. So as you can imagine, this is what as the ATM community want to achieve, that all aircraft end up flying continuous climb operation and continuous descent operation. So there was a study done by Eurocontrol in 2018 in all the countries of the ACAC, and they found that for the continuous climb operations, they concluded that 94% of flights in the economic European area currently fly continuous climb operation to fly level 100, and 74% fly with full continuous climb operation to the top of climb. And these numbers are quite big. 74% of flights flying continuous flying operation, it's a big achievement, and that's something that Europe and CESAR have been working on, and I think it's giving some benefits already. Then from the continuous descent operation, on the other hand, they found that this number was much lower. They concluded that 41% of flights fly continuous descent operation from flight level 75, which they identify as the top of noise DDO. And only 24% of the flights fly continuous descent operation from the actual top of descent, which they call the top of descent of the fuel. So they identify two tops, as to say the lower one, which is the noise one. I assume that over that flight level 25, the noise is not too disrupting to population. And the actual top of descent, which is the one that we defined in some slides before, is the actual point from which the aircraft start to descend, which is what is important in terms of the fuel. So they found that actually from the top of the descent, only 24% of flights do a continuous descent operation. So there is still a lot of work to do with continuous descent operations. There were two main conclusions from the study. First, that the potential savings from optimizing continuous climb operations and continuous descent operations are up to 340,000 tons of fuel per year. This is equal to 150 million euros, or the equivalent to 1.1 million tons of CO2 released to the atmosphere. So there are a lot of potential for, so the potential benefits of performing continuous climb operation and continuous descent operation are a lot. So we should, the ATM in Europe in general should be aiming for doing this kind of operations around airports. And finally, they conclude that the potential fuel saving benefits from CDO are in the region of 10 times those from CCO. I assume because there are a lot of potentials, a lot of work still to do in CDO operations in concern with CCO. But as you can see, this is a very popular topic, I would say, a very relevant in ATM because it has a lot of potential benefits and is already being implemented. So that's good. So this is what a global optimization, a global trajectory optimization trajectory could look like, considering what we saw. This is the black one is the traditional trajectory profile. We have stepped climb that requires an increase in fuel consumption, and this is not efficient in terms of fuel. Then the cruise is done at a constant altitude. As we saw, this is not the most efficient thing. The most efficient thing to aircraft to do in cruise segments is to increase the altitude as their wave goes down. And finally, the descent also is done traditionally in steps, which results in unnecessary fuel burn. On the other hand, we have the optimal profile. The optimal profile will look something like this. We have a continuous climb with constant acceleration. The fuel is used to gain distance as well as to climb. Then we have a smooth transition between climb and cruise. And in the cruise, we have a cruise climb, where the altitude increases as aircraft mass falls. And then we reach the top of descent, at which point we put the engines in a idle position with minimum fuel consumption, and we descend in idle descent angle. So this is what an optimal profile would look like. So the objective right now, as of today, is to complete the climb and descent using continuous climb operation and continuous descent operation. The cruise climb part, I think, is a little farther in the future, but still doing the climb at optimal flight levels is still an achievement that I think there are a lot of ANSPs that are working towards it. So yep, this is what a trajectory could look like. This is what they look today, and the optimal one. So you can see it's a little, it's all very smooth, very theoretical, but the good part is that aircraft can actually fly these trajectories using the computers on board. So if they were alone in the airspace, they could fly optimal trajectories all day long. But because air traffic, because the number of airplanes in the airspace is a lot, that's what is restricting those trajectories to not those aircraft not to perform optimal trajectories. So this is not a technical problem. Aircraft can fly these trajectories as of today. It is an ATM problem. It's a demand. It's a capacity problem. So it's ATM the responsible for trying to mitigate these inefficiencies in fuel consumption. Yes, so that's all for trajectory optimization. I'm going to talk a little bit about aircraft conflict detection and resolution, and also about trajectory optimization and their methodological conditions. They are going to be just a couple of short slides, but as I just said, aircraft trajectories are already optimized. They know how to fly those trajectories. So our task as researchers or as workers in the ATM is to accommodate those optimized trajectories to the constraints that the ATM system imposes. And one of those constraints is the conflict between the aircraft. So because aircraft do not fly along in the airspace, we must construct trajectories that are conflict-free. So I will give you the definition of a conflict. A conflict between two aircraft exists when a set of separation minima is predicted to be violated in the future. That means that we have an horizontal distance requirement, which is usually it's usually named with the letter D, and a vertical distance H. So you can think that the aircraft are surrounded by a protected zones, and those zones must not overlap. If this protected zones overlap, we say that the aircraft are in conflict. Or if these protected zones are predicted to overlap in the future, we say that the aircraft are in conflict. So the work of an air traffic controller is to prevent these losses of separation to occur, is to prevent these conflicts to occur. So aircraft trajectory optimization must take into consideration that the aircraft trajectories must be conflict-free. So operationally speaking, this can be done by, for example, assigning a given high level to the aircraft. For example, you have an aircraft flying north to south and another flying west to east, for example. I don't know. And you put one in one high level and on one fly level and another in a lower fly level. Those aircraft are not going to be in conflict because they have a vertical separation greater than their separation requirement. So that's one way to do it. But if we want to optimize the trajectories, if we want to fly with continuous climb separation, we want to fly with cruise climbs, we have to take into consideration other kind of techniques, other kind of measures to prevent those conflicts. So this could be an example of the optimization problem as we saw in class, but now for multiple aircraft. So the inputs are the same, but we have added a new input, which is that now we have, instead of one aircraft, we have a set of aircraft, which goes from 1 to n. The output is the same. We want to obtain the optical Mach numbers and the optical altitude profiles for all aircraft. But now we have added a new constraint, which is that the aircraft trajectories must be conflict-free. And the objective function, instead of being the direct operating cost of one aircraft, is the sum of the DOCs for each individual aircraft. So we have the more important changes that we made if we have to consider multiple aircraft is that the aircraft trajectories must be conflict-free. And this is not an easy topic, because in scenarios where there is a lot of traffic, demand, or a lot of traffic in general, this can be very difficult. And in some cases, they might be even impossible. So we have to, this is where air traffic flow and capacity management comes into play, by delaying some flights or rerouting them. So this is a very relevant topic to optimize trajectories while also maintaining the safety in the airspace by maintaining conflict-free trajectories. This is an example of a paper that tackles trajectory optimization while also having conflict-free trajectories. This is an example that considers optimal conflict-free trajectories in a terminal maneuvering area of an airport. So we have the terminal maneuvering area, with which is depicted in a little blue lines. Then we have all the waypoints that are inside this terminal maneuvering area. So the output of the problem, of the optimization problem in this particular paper, is are the coordinates or the trajectory waypoints. So the output is a sequence of waypoints that the aircraft must follow, and the objective function is the deviation from the nominal trajectories. They consider that the aircraft trajectories are already, if the aircraft were to fly along in the airspace, they will have a nominal trajectory that is optimal for them. So what they want to do is to minimize the deviation from the resolution trajectories to those nominal trajectories that are already optimal. So they come up with trajectories that are like this, as you can see. So these little circles, so the asterisks are the positions of the aircraft, and the little circles around them are the protected zones. If this, I remind you, if these protected zones were to overlap, we will have a conflict. So you can see that as time passes, the aircraft follow a given trajectory. We have a converging point over here. And we can see that the aircraft maintain their separations. And supposedly, these are the optimal trajectories. So this is what the problem from the literature looks like. There are a lot of research done in this topic, and also is being done as we speak, because it's a very relevant topic and it has a lot of potential benefits for ATM. And then finally, we have trajectory optimization under meteorological conditions. So as you know, weather is very significant in aviation, in aspects like safety, and what we tackle in this lesson, efficiency. So aircraft trajectories are going to be affected by meteorology, by weather, and there are two main weather phenomena that affect the trajectories. First, we have winds. The winds affect the aircraft trajectories by modifying their ground speeds. So basically, an aircraft has two speeds. First, they have the airspace, which is the speed of the aircraft with respect to the air, with respect to the mass of air that is surrounding the aircraft. And that is what the aircraft feels, so to speak, is what the engines feel, is what the engines are working against, is what the density of that air is, the one that's feeding the engines. The velocimeter in the avionic panel is going to indicate that airspeed. And that's what imagine a boat. The airspeed would be the equivalent of the velocity of that boat with respect to the water. And then we have the ground speed. The ground speed is the speed with respect to the ground. So that could be the thing that we would observe from the ground if we look at an airplane. And the difference between the airspeed and the ground speed is the wind. If you have a wind that is coming from the back, that we call that a tailwind, we will have a bigger ground speed than we have airspeed. On the other hand, if we have a wind that is coming from towards the aircraft, we call that a headwind. The aircraft will feel like it is slowing down. The airspeed is the same in both cases, but the ground speed are not. And this is very important because we want to fly from place E to place B, but those A and B points are in the ground. So we want to look at our direction above the ground, because finally we want to get from one point to another and not just drift into the air. If you think, you can think of this as a boat. As I said, we have the knots of the velocity of the boat that is measured in knots, and if they know not, if the crew don't see the land, the only velocity that they consider is the velocity with respect to the water. But if there is something that is drifting them, like for example winds, or there are some water movements that are moving the boat without the crew seeing it, the boat could drift and eventually end up in some place that they don't intend to. So this is kind of similar what happens to airplanes. Of course, we know where we are because we have GPS. We have, if we are flying with a visual flight rules, we have the visuals from the ground and from the geography. But we have to consider that the wind is going to affect our final destination or speed with respect to the ground, etc. And also we have another important weather phenomena that affects aircraft trajectories is adverse weather zones. Maybe because we have some kind of convective activity. It can be because we have volcanic ashes or turbulence. So these are parts of the airspace that are occupied by bad weather or severe weather that we want to avoid. So these two weather phenomena affect a lot the aircraft trajectories. So let's start with the wind. If we try to incorporate winds to our optimization problem, of course, it will come as the form in the input. We will have to consider not only the atmosphere and the aircraft models and the equation of the flight segment, etc., but also as an input, we would have to consider the wind map, what the wind looks like, what the wind that the aircraft is going to encounter, it's going to look like. And also, this wind needs to be incorporated in the model. So the direct operating cost must take into account the influence of the wind. This is an example of a research that was done in this by studying minimum fuel trajectories over the Atlantic Ocean. So what we see here in black over here, this is the shortest path between Rome and New York. So this is the great circle. This is the shortest path that the aircraft can fly. So if you can think that if there were no winds, the optimal trajectory, the optimal horizontal trajectory could be this one over here, the black one. But we can see that if we are flying from New York to Rome, the optimal trajectory, if we want to save fuel, actually is this red one over here. So we can see that it goes a little farther north than the actual great circle, and we can see that it's taking advantage of those tailwinds in order to use less fuel. And at the same time, if we want to fly from Rome to New York, the optimal minimum fuel trajectory would be this blue one over here, which is very different from these other ones. They want to avoid the headwinds in order to not be slowed down. So they fly over here where the winds are not that detriment to them. So the optimal fuel trajectory would be this one over here. And then you can see that it's quite, these routes are quite different. So we can say that the winds are quite important when planning aircraft trajectories in general. And one thing that it's very relevant today that is taking a lot of, that it's, how to say, that it's very, that it's being studied a lot in ATM today is how, because those winds, the only way to know them before you take off is with a weather forecast. And weather forecasts are not always right. There are some kind of uncertainty present in this weather forecast. So one line of investigation that is very relevant today is to study how this uncertainty in the weather forecasts affect the optimal trajectories. So maybe you can say, okay, my optimal trajectory is over here, but I know that these winds are uncertain. So maybe we have a probability that this is not the optimal trajectory. So this is something that is being studied today. Has a lot of, I think it's as our solution, it's based on this concept of including in uncertainty in meteorological conditions on aircraft trajectory optimization and in trajectory-based operation in general. Okay, so let's finish with adverse weather zones. So as I said, adverse weather zones are something that are regions of the airspace that the aircraft wants to avoid because there are some safety issues if we enter those zones. For example, we could have turbulence, we could have hail, we could have any other weather hazard that can affect the aircraft. So it's better that we don't that the aircraft trajectory do not intersect these adverse weather zones. So if we try to include adverse weather zones in our optimization problem, we would have to include them as an input. So as an input, we would have a set of polygons that represent the adverse weather zones. In this figure over here is the polygons in red. And I messed up because this needs to be in constraints. So the output is a set of functions, blah, 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 and this blue one is over here. Sorry for the mistake. I will correct it before uploading it to the web page. So we must add an additional constraint, which is that the aircraft trajectory must not intersect the adverse weather zones. And how to do that, how to deviate from those weather cells, it's again something that is not easy. It's something that's being that is a topic now in research. So if you want to know more, just go to the bibliography or ask me about it. There are a lot of topics around a lot of research done around these topics about weather in general in aircraft trajectories. So yeah, that's it. And that's it for today. This is the bibliography and the online resources that I used. And that's all on my part. So do you have any questions for today? Okay. I guess that means that you don't have questions and that everything's great. Do you have any questions about the project or the homeworks?
Not
Yes.
now.
Kör du först, Erik.
Nej, jag sa bara, I don't have any.
Okay. So we can't do, as you said, we shouldn't do anything from what we did in homework 1, but So we have to find a subject which isn't made of any of the persons in our group from homework 1 in the group project.
No, so it mustn't be the same problem, but you can work with around that topic. So if you made your work on, I don't know, on TMA on homework 1, you can still work with that topic. What you cannot do is use exactly the same optimization problem. So you can add to that problem, or you can make some simplifications, or just make something new. You can use the same topics. So if you want to use those same topics that you use in homework 1 or 2, feel free to do so.
Okay, thank you.
Well, I guess that's it. See you then.